Hello, we are starting topic 9, the last topic in this course. And this is actually to kind of conclude the work we have done and kind of introduce you to what's coming next. Okay. What we have done so far, we have talked about combinational elements that fit in an RTL design, sequential elements that fit in in an RTL design, sequential things like registers, counters, shift registers, the combinationals, things like ALU, comparator, and adders and multiplexers. Then we also talked about the interconnections, and then we said that there is somebody controlling all of this, and that's the controller. We did the controller. And then the last thing we did was we did a serial adder saying that bits are received on A and B, and we developed a circuit that will take these bits and then bit by bit add them into an 8-bit result, and then issue the result, and also issue a signal indicating that all the work is done. That was an RT level design. It was a very simple one, but it was an RT level design. So what I'm doing now is doing something a little bit more complex, and then something a little bit more complex in this part. So let's start with this. What I'm doing is a multiplier. Okay, see, I can do a multiplier like this. I can do an array of multipliers and adders, where my let's say A input, let's say 4, 5, 6, 7, 8, and then we have 1, 2, 3, 4, 5, 6, 7, 8. So this is an array of 8 by 8. This is called an array multiplier that has adders in each of these rows. So it has 8-bit adders that are being used to add the data that come in from the top. So what I'm saying is it's an 8-bit multiplier producing 16-bit results, and the 16-bit results will be will be formed by these adders that are there. So what I have to have 8 rows of 8-bit adders put in diagonally. So that works, but then the problem is that I have 8 8-bit adders for operands of 8-bit. This is A, this is B, both of them 8 bits, and then I have this. So, like I said, it works, but the problem is you are using this many adders. You're using this many adders to perform this adding, and then take the result down to the next adder, then the result down to the next adder, and so on and on. So something that comes to mind is why do that? Why not use one adder and take the result, and then on the next clock reuse that adder and do the next cycle, and then instead of what I'm showing here, which will be taking one clock cycle, this is a combinational within a clock cycle, this is done. I will be doing it in 8 clock cycles, first one, second one, and so on. Conceptually like this. This is not going to happen like I'm saying it now. But then the fact that instead of using one 8 adders, let's use one adder, and instead of propagating the results, let's clock them into a register, and then let's reuse that same adder. That's a good thing. Actually, what we did for our serial adder that we did before, we did something like that, right? Because there was this serial adder that we were building. The adder was supposed to be an 8-bit adder, but then what we did was we took a full adder for the serial in, A in, and B in. These are each 1-bit things. And then the output was collected bit at a time, and therefore what we did was we only used one full adder, and this was the carry. One full adder to take one result and then take the carry for the next bit, for the next bit, and for the next bit. Alternatively, if A and B came in parallel, 8-bit data, then I had to have an 8-bit adder to do the same operation. So what I'm really using is I'm reusing the full adder over and over and over in 8 clock cycles. What I'm talking about here now is something similar to this. Okay. This was, of course, an adder. Now I'm talking about a multiplier. But then I'm saying let's do it in a sequential circuit, so that I don't have to have these many adders. So this is what I'm going to be designing. I'm going to show you 4-bit just so that the it's simpler. It's simpler to look at, but then you can easily turn what I'm showing you here from a 4-bit adder to from a 4-bit multiplier producing 8-bit results to a 16-bit multiplier producing 32-bit results. The bigger it gets, this technique I'm showing makes less sense. Okay? Becomes more impractical. I tell you why. The multiplier begins after a positive pulse on start. What it means is the clock must be seeing a 0 here, must be seeing a 1 here, and must be seeing a 0 here, and then things begin. After that, data from A bus and B bus are collected in my multiplier. This is what I'm multiplying. So A multiplied by B, A and B will be simultaneously available after the edge of the clock. Okay, that after the edge of the clock that sees the 0, the next cycle will be seeing A and B, and then we will clock them. Because when something comes on the bus, you better get it done when they tell you that is valid, because next clock may not be valid. Maybe the bus is given to somebody else. So I take A and B, and then notice that the circuit is clocked, but I don't really have to worry about the clocking here. And the clock and reset don't interfere in my design. They are there, they're important, but my design procedure assumes they're always there and I don't touch them. So start comes in, and the multiplier starts multiplying. When it's done, it shows done equal to 1, and then done becomes 1. Done becomes 1. Somebody looks at it from the outside. As soon as it sees done is 1, it says, oh, okay, the 8-bit result is good. So you can pick it up while done is 1. Somebody else can look at the done signal and say, well, this is done with the old result, or with the old data that I gave it to perform the multiplication. So I can give it another start pulse and new data. Okay, so done serves 2 purposes. One is, okay, take the output. Output is good. Secondly, I can accept new data for multiplication. All right. There are good multipliers, and a lot of work has been done on multiplication, and courses on computer arithmetic. They do a lot of high efficient techniques for multiplication. I'm not doing that. I'm doing a very, very simple, in a way, not obsolete, but in a way, an algorithm that is not efficient, but it's good educational algorithm for doing our very, very first RT level design. Okay, it's really no algorithm. It is what we have already seen. See, when you want to multiply A and B, one way is to say, let's add B to the multiplication result a number of times. That's it. That is the simple, too simple, and non-efficient algorithm that I'm going to be implementing. Once again, I say that. Let's add B to product a number of times. Okay. So if A is 5, B is 9. Okay. Let's add B to the product becoming initially being 0. P is initially 0. Let's add B to P. The first time you add is 9. The second time you add is 18. The third time is 27. Finally, after 5 times, it becomes 45. And this is my algorithm. Why have I chosen such an easy algorithm? Because right now, without showing you the hardware, we can all come up with the data path and the controller of this circuit. For the data path, we are doing 4 bits, right? The result has to be 8 bits. So I have a product register, a register. Okay, I'm thinking about hardware elements, hardware components, hardware elements that I'm familiar with already. I have a 8-bit register that I call it P that collects the product. Okay, initially I set that to 0. See, all I'm talking about are components that we have discussed. We are talking about control signals that do things. Initially, it sets it to 0. That means there is an initialization signal for P. Then it says, add B to P. That means, okay, P is initially 0. B is loaded in a 4-bit register. Let's add these two things together and put the result in P. Okay? But then we have to control how many times this is going to happen. And that how many times has to do with A. So visualize the hardware that we will be designing for this. Without fast forwarding the video, let's think about the hardware. So the hardware is, I do a draft of it here. So is a P register, which is a 8-bit register, goes into an adder, and then there is the B register, which is a 4-bit register. Okay, and then the result of the add is 8-bit, and that 8-bit goes into the P register. And I have to repeat this a number of times. So why not put A in a, no, this is my B bus coming into B. And then I have another register, which is my A register, and I have the A bus going into that, and that is a down counter. Each time I perform this adding and clocking information into P, I decrement my A counter, and I continue doing this until A reaches 0. When it has reached 0, I say that I have done enough of adding B to P, and therefore P at this time will have my final output. I designed it. I designed the whole thing by these statements. See, I came up with the procedure. It was a nice procedure. It was an easy procedure. Okay, the good thing about the procedure or the algorithm was that I could just write it down and then write down corresponding hardware components to it, which is these hardware components. This becomes the data path of my design. More details than the little thing that I put over here. I have an result register, which I'm calling it, which is an 8-bit register, 8-bit, okay, which is providing my result. This register has an initialization because I have to initialize it. Because if new data comes in, I want to make sure that this product that we're adding to it starts with 0 and not with the result of the previous product. And therefore we have an initialization. Okay, and that goes into an adder, which is good because that's one side of the adder is this register. The other side of the adder is the B register because B has to get added to that register a number of times. But then that is 8-bit because the result of multiplication can go up to 8 bits. My B register is only 4 bits. And therefore, I have appended 8 zeros to the left of my B. And therefore, an 8-bit adder adds these two, produces an 8-bit result. That 8-bit result gets clocked into the product register, the result register. And so that's that path. I'll come back to the control signals in a few seconds. Then I have the B register. The B register connects to the B bus. The B bus is 4 bits. And then remember we said that at the beginning when the start is issued, I'll have to load from data bus or from B bus into the B register. And therefore there is a load control signal, load B, and that is the control signal. Comes from the controller. We are not discussing them here. Then I have to count how many times I'm adding P to or B to the product. When A bus comes in, it comes in into a register. Okay, gets clocked in there. That register turns out to be a counter, a down counter. Each time that addition, each time this addition and clocking into this register is performed, a register is decremented by 1. And then decremented again until it says I have decremented to 0. It tells who? It tells the controller. At that time, the controller says, okay, we have done enough adding of B to P. Let's stop it. We have the correct result. It issues done. Okay? We get to the controller in a second, in a few minutes. But then let's do the control signals here. The control signals I have, init R, because I have to initialize it. Load R, with every adding, I have to do the loading. Because the adding happens, it's combinational, but then unless I capture the output of the adder, it's no good. And how do I capture it? I capture it with load R. Then I have the B register here that initially I loaded and I don't touch it. Then I have the A register, which is a counter. Initially I load it. And once I load it, I need to control it and count down, and this. And then we have a control signal that goes out, and that is the control signal that tells the controller that these guys have done enough adding, and it's time to declare the output is ready. And see the two buses. This is one bus. This is the other bus. These are the input buses. And then this is the output bus of my circuit. And That's all there is to it with my data path. And now before going to the controller, let's do the data path Verilog description. Okay, just look at this, and then we describe this exactly as is. See, the schematic is what is important. I did this. I did the design. Going from this schematic to Verilog is just like this. Verilog is not the important part of your design. Verilog is just one way of you representing your design. I have already represented my design like this. Okay? What I do, all these orange buses and all these blue buses and all that, they have to have names. Some of them, the blue buses do. The A bus, B bus, R bus. But then the output of the B register has a name. It's called B reg. But then the output of the adder, because I have to identify it and connect it to the input of the R register, it has to be named. I'm calling it the add bus, the 8-bit add bus. And then I will do my Verilog. Okay? Just close your eyes and describe this in Verilog. Nothing. It's an assign. Add bus equal reg plus curly bracket 4-tick B0 B reg. This thing down here. Okay? That's all. So take each of those components after you have named all their inputs and outputs, and then write a few lines for them. Some are a little bit more complex than the others. Okay? And this gives me the data path. Okay, so let's start with the data path. The data path has input, clock, and reset. Also, it has control signal inputs, load A, load B, load R, init R, count down, and that's it. Who provides this? The controller provides this. And then I have a 4-bit input A bus, another one B bus. Okay, that's line 2. My output is an 8-bit result bus, and then my output is 0, but this output is really not output of the whole circuit. It is the output of the data path only. So what I'm really doing here is, look, what I'm doing here is this is the data path. It takes A bus, B bus. It produces the 0 flag to the controller. Controller has a start done. It issues the load A, load B, load R, init R signals to the data path, which is this thing here. And then this is the control unit. Both of them have the same clock, and both of them have asynchronous reset. And 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Signals from the control unit to this. This is the A bus. This is the B bus. And then finally I have the output, which is called result bus. Okay, which is an 8-bit. And okay, now I'm focusing on this, which is this. All right, let's go back and talk about this implementation. What's inside this? I already shown you the add bus. Let's talk about the reg. Reg is a register, and therefore I have to declare it as reg 15, not 15, 7:0 reg. Okay, this is reg. Okay, I have A reg, I have B reg, and I have a counter. Okay. I don't need a reg, and I'm not using it. Okay, actually a reg is the same as the count, and you will see that I'm not using it. Okay, and then I have add bus, which is the output of the adder. Okay, now let's concentrate on doing the registers, the interconnections, and also the combinational parts. We have actually done one of the registers already. So let's do the which one is first one? Let's do the B register. The B register is green, and so let's do this. Okay, this always a statement here. Positive edge clock, positive edge reset. If reset is 1, put 4 zeros in B reg. Otherwise, if load B is 1, B bus goes into B reg. Okay, I'm done with this. And now go into the next register, which is the R register. This is the R register. The R register requires clocking and resetting. Well, they all require clocking, but then they clocked resetting, which is the initialization. So you're seeing that on line 17, I start with always, if init R is active, put 4 zeros into R reg, otherwise put add bus into R reg. Okay, R reg is, let's go up here, R reg is 8 bits. So why do I have 4 bits here? On line 19, R reg gets only 4 bits. It's true, it's my mistake. Okay, but it's a mistake that Verilog forgives. Verilog says, well, on the right hand side you put 4 zeros, the left hand side is really 8. It makes a decision for me that I made a mistake, and therefore this 4 tick B0 on line 19 expands to 8 tick B0. True that Verilog helps me out here, but don't do that. Okay? Because some other cases, Verilog may make decisions for you that you don't really appreciate. And therefore, best would be to make this one 8 tick B0. Okay, 8 tick B0. All right, that's the period, the R register. Okay, and the R register provides the output for the result. I'm done with the R register. Let's do the third register, which is that A register, which is the counter. Okay. Instead of calling it A reg, I'm calling it count. Okay. Same thing. And this is blue, so I'm doing this in dark blue, which is this. Okay. Again, positive edge of clock, positive edge reset, or pause reset. If load A is active, put A bus into count here. If load A is active, put A bus into count. That's line 28. Else, if countdown is 1, who issues countdown? This guy over here, the control unit here. One of these signals going to Datapath is countdown. If countdown is active, the count register gets decremented by 1. If it's 15, it will be 14, 13, and so on. And then this continues. And then down below on line 34, I have if all bits of count are 0, or if none of them are 1, then the 0 flag becomes 1. The 0 flag is this thing over here that goes out. So the zero flag is actually part of this counter, but because it's a combination part of the counter, we usually use assign statement out of the sequential block that does the counting. So let's go back up here. I'm done with all of these. Actually, I did the adder right at the beginning, which is this color now. And am I done? Yes, with one little thing here, and that is putting the output of reg into result bus. And this one is this thing down here. Okay, line 36 says assign result bus equal to reg. If you want to see it better, this is the line above it, and this one is the okay. So this is my data path. I'm done with my data path. And notice that it wasn't a very difficult data path once you have this. And this is not very difficult once you have the algorithm. The algorithm is what is difficult, which I chose a very, very simple one, a very bad one, of course. This is bad because for multiplying a 4-bit number by 4-bit number, it will take up to 15 clock cycles. There's a possibility, because I'm decrementing A, I'm adding B to P a number of times. If A is 15, it will take those many clock cycles. Okay? And if I have a 64-bit multiplication, then there is a possibility of 64,000 clock cycles for that. That's impossible. Okay? This is not a good multiplier. Practical. Educational, this is perfect because this is our first example and we're learning from it. All right, how about the controller? The controller, look, it's just like a state machine you have seen already. Waits for a start signal. Wait until the start becomes 1. While we are in the start, it keeps issuing done equal to 1. While when the start becomes 1, it goes into the initialization, waits for the start to become 0. While there, it waits for the start to start. It loops back into the same state for as long as the start is 1. And then when the start becomes 0, it goes into the load state. Load state loads A, loads B. The initialization signal is a good place for initializing my registers. That's where I'm initializing the init R. That's the result register. Of course, I could do it over here as well. Doesn't matter. But then, with this procedure of having one complete positive pulse for the start, right at this point, when the start becomes 0, you go to the load state, and in the load state, you issue the loads. You still have that prior state, the init state, that if there are other things that you need to do, you could do that too. Okay? So maybe you wanted to, if there were things that you were doing with the register A and register B, you could probably do it in the init state. All right, for as long as there's no conflict, you can do them all in one state. And then you go into the counter state. The counter state waits for the 0 flag to come out of the counter, okay, which is this thing over here. Line 35. No, line 34. So he waits there until the 0 flag becomes 1. For as long as 0 flag has not become 1, for as long as 0 flag is 0, it's still 0, it performs counting down. That means the A register keeps counting down, down, down. But when it reaches 0, there is no more counting down. It's just 0, and therefore the countdown is not issued anymore. At the same time, load R is being issued. Load R, load R, load R for as long as 0 flag hasn't been reached. When the 0 flag reaches, then you will not count and you will not load. You say, well, I've counted enough, I've loaded enough into the P register, into the result register. 0 is 1. Let's go to the idle state, not touch anything, because the result is good. Issue done. And then wait there for the next round. Okay? And that is the controller. Okay, do I need to write Verilog? Only if it's required. But see, the state machine is all you really need. The same way this schematic is all you really need. This is all you really need for the implementation. Okay? For the design. For the implementation, yeah, let's do the Verilog. Multiplier control unit. Clock reset the inputs. Start and 0 the inputs. Start from outside world, 0 from the data path. Load A, load B, load R, init R, count down, and done are the outputs of my controller. These outputs of the controller are being assigned values inside all of the statements, and therefore I call them reg. I declare them as reg. I have a the way I'm describing this is Hoffman model. So there is a combinational. The load A, load B, load R, init R, count down, and done are all issued from the combinational. The inputs are start and 0. Start is coming from the outside world. 0 is coming from the controller, from the data path. Okay, this is the control unit that I was showing in one of the previous slides. This one here. Okay, now I'm looking inside the controller unit. The control unit has a 2-bit present state, next state. This is Hoffman model. This is the present state, and this is the next state. Okay, 2 bits. I'm declaring a parameter idle init load count. Idle init load count. The name of the state, so that when I write them, it will be more appealing, more stylish, more readable. Okay, this is the control unit. This, it's always good to show the correspondence of the blocks and the codes. This is this. Okay. It has the P state as input. See, P state is input. It has the 0 coming from the data path as input. It has the start coming from the outside world as input. So they are in the sensitivity list. The outputs are next state, which you are seeing the output. The outputs are next state and all those signals. In order to stay on the safe side, all the outputs are set to their inactive values at the very beginning of the always the statement. So line 8 and line 9 set all these outputs to their inactive values. Then case present state. If I'm in idle, next state becomes just follow the state diagram. See, let's look at line 11. Okay, and this is this. So if you start is 1, I go to init. Here, If the start is 1, I go to init. Otherwise, I stay in the same state. And then my done is also 1. I repeat this same exact thing, or this same exact procedure. I repeat that for the next state and the next state and the next state. Let's look at the load state. The load state, the next state is count unconditionally. The next state is count unconditionally. Look at this line here, line 13. The next state is count unconditionally, and then I also issue load B and load A. And then you see those in the in that state, in the load state. And then finally, the count state is issuing load R and count down only if the 0 flag is 0, and which means count down equal to tilde 0, which is what I have over here. Okay, which is what I have over here, which is this. All right, so what I'm really showing is that the state diagram is the whole thing, and then you just have to turn it into the Verilog code. And then line 15 says default end state is idle, end case, and always. And then comes the easy part. The easy part is the register part, which is this. The register part, all it says is on the reset, idle becomes the present state. Otherwise, next state goes into the present state. And this is the control unit description. I put these two together, okay, and then write the test bench for it. This is multiplier top. I'm not showing it. It just corresponds to this wiring. Okay, corresponds to this wiring. It has the result bus, A bus, B bus, clocking and resetting, and the external control signals. And then here is a test bench, a clock, a reset, a start signal, A, B, the result, and the done wire. Now, why is done wire? Because it's the output. The rest of them are, I'm assigning values to them. Those are all inputs. Actually, result bus is, of course, wire also, because that's also output. And then I associate the clock, reset, start, A, B, result bus, and done with the inputs and outputs of the top level multiplication unit. This one, line 13, every 5 nanosecond clocks. Starting line 15 to line 27. It's an initial statement. In the initial statement, I'm resetting, I'm putting something into A, putting something into B, starting, ending, and then line 22, put some value on A, put some value on B, and then start the multiplication, and then 10,000 clock cycles later, you stop. And then you look at the waveform. This is the waveform. Look at some of the results. Fortunately, they work. Here. 4 times 11. But then it takes 11 clock cycles. Let's see how many clock cycles it takes. After start, 1, 2, 3, 4 clock cycles. The reason is 5 clock cycles. Okay. It takes 5 clock cycles because A is 5. Remember, we said that the B is added to the product A number of times, and therefore 5 clock cycles. Okay, the value A is 4. The value B is 11. And no, it takes 4 clock cycles after start. 1, 2, 3, 4, and then on the next clock, on this next clock, see, after start, the next rising edge is ignored because it only sees the 0 start. Then I have 1, 2, 3, 4. This one is loading, and then these 4 are counting A, and this is where my result shows up. And the next one is 5 times 9. It takes more clock cycles, and then again you have to wait for the start. After the start, then 5 clock cycles, and then 45. All right, we have tested our multiplier. It's not a very smart multiplier, but it's a first multiplier. We can do better. Okay? I discuss that next.